You'll have to look in both. Hababeda, I don't think you're allowed boots. Bismillah ar-Rahman ar-Rahim. In the name of God, the most gracious, the most merciful. Welcome for finally joining the lesson, Advanced Integration. It's some of the advanced topics within integration. You're still doing integration, but it'll just look a little bit harder and you need to know the techniques to be able to do that. So let's begin with a quick game of noughts and crosses to warm you up, inshallah. Okay, Bismillah ar-Rahman ar-Rahim. Okay, one of you can be circles and one of you can be crosses. Only seeing one of you on the screen. Okay, no worries, we'll just carry on. So you can go first, choose any way you like, and then draw a nought or a cross. Just check if it's working as well. Okay, good. Back to you. Over to you again. Okay, looks like it's going to be a hard one to win for me. Let me try here. Okay, didn't quite win there. Let's go over down here in this corner. Okay, well done. I think that's a victory for you. Oops. Let me just take control off. Okay, well done. Inshallah, integration will be just as easy, but you just have to follow the steps. So we'll start with a quick warm-up just to make sure that you're okay with the basic ones. So just try these three. Integrate 2x squared dx. dx just means with respect to x. And then if you're a bit more confident, try the next one as well. Integrate sine of 3x. Okay, I'll just give you 2 minutes on that. Okay, once you're done, feel free to type in your answers into the chat window. Okay, the first two are basic ones, and you should be comfortable with them. If you're not, then you have to say otherwise. The rest of the lesson will be too advanced for you, and you need to go through these two first, which we can do, inshallah. Well done to Aisha for the first answer. So add 1 to the power and then divide by the new power. That's the first one. We can put a plus C. It's not really necessary at the moment. And then the second one is minus cos 3x. And then you have to divide by whatever 3x differentiates to, which is 1 over 3. So almost there. Just be careful on the minus. If you're not sure on the minus, whether it's put minus or not, just go back to the basics. Just do a little table for yourself. Sine differentiates to cos. So that means cos would integrate to sine. And then so no need to change the sign or on either of that. When you're integrating cos, no need to change the sign. But if you then look, okay, what about cos differentiates to minus sine? So then realize that you need to change the sign when you're going back and you're integrating. Okay, just type in yes or no if you're comfortable with both those answers. Aisha, I think you are. If you can just type in both. Okay, good. So then you should also be comfortable with the third one as well, even though you might not have done it before, because there's no advanced technique here. You just need to integrate whatever it says. And just because you haven't seen it before, you haven't seen the integral of cot, that's fine. Just check the formula booklet. That's why the formula booklet is there in your exam, to let you not have to worry about the ones that are slightly harder and you wouldn't have done that many times. So here we can see in the integration section of your formula booklet, if you just skip down, it says here, if you're trying to integrate tan, then the answer would be this. Here we were trying to integrate cot of 2x. So cot is the main thing we need to look for. So we see that cot cotangent integrates to the natural log of sine x. So that's what you just tried to remember. So this will just be, will integrate to the natural log of sine x. So you're just using your formula booklet. Because the question had 2x, then instead of putting sine x, I'll put sine 2x. And then just like here, when you were integrating sine of 3x, you had to do an adjustment. So you divide by whatever the 3x differentiates to, that's 3. So it's 1 over 3. So similarly here, we've got 2x in the brackets. So when we're integrating, we just need to put a divide by 2 at the beginning. So that would be a half at the beginning, 1 over 2. Okay, you try one just to make sure you're happy on that. So let me give you the integral of tan x. Let's try the integral of tan 3x and see if you can use the formula booklet to figure that one out. And if you finish that one quickly, I'll give you another one. Okay, feel free to try the second one if you're already done the first. If you're still on the first, that's fine. Just carry on working on that. Okay, well done. Looks like you're ready for answers. So just check your first answer if you've done the first one, and check both answers if you've managed to do both. And on the second one, just let me put the fraction at the beginning. So 2x plus 1 differentiates to 2, so it's 1 over 2. Okay, good. No worries if you haven't got the modulus bars, that's fine. Okay, good. All your answers are good. Just remember that for harder questions, we would need to put the plus c at the end, but for now, that's fine. Okay, good. Bismillah ar-Rahman ar-Rahim. Let's begin our first main topic within integration, advanced integration. So this is called integration by substitution. Integration by substitution. And the idea is that the integration is not just a simple thing. If the integration was just 2x plus 5, you could do that easily. If it was just the integration of x, you could do that easily. But here it's a combination of a couple of things, and there's a square root in there. So it's pretty tricky when you first look at it. So the idea is that in the exam, for the simpler ones at least, they will give you a substitution to make that will make it easier for you. So they will say, for example, use the substitution that for 2x plus 5, wherever you see 2x plus 5 in the question, just substitute it with u, the letter u. And for harder ones, we'll have to think of the substitution ourselves, but just to begin with, just to build you up, the ones we'll look at is where in the exam they will give you the substitution. They'll say use 2x plus 5 or swap 2x plus 5 for u, and that will make it easier for you. So we can do that straight away. There'll be a bit more work to do as well, but let's see how that looks. And what we want to try and end up with is something that looks much, much easier to integrate. So we'll copy everything, the integral sign, the x, but where we see the 2x plus 5, we are going to swap that for u. So that just becomes the square root of u. And you can see that's looking much, much nicer now, much, much easier. And then we copy everything else, which is dx. Okay. The next thing we want to do is really make sure that everything is in terms of u, not just have part of it with u and the other parts of x. So we take a look at the other parts and think, okay, this x has to be swapped as well. So we go back to this equation and we could rearrange it so that we've got something to swap with the x. So if I just rearrange this, I'll have u take away 5 is equal to 2x. And then if I divide both sides by 2 or times by half at the front, then I'll have half u take away 5 is equal to x. And just to remind you, I think you've attended a couple of these sessions, so always I'll go through an example first fully, and then you'll get a chance to try yourself. So don't worry too much if it's a bit of listening at the minute, but just trying to make sure that you see it all done. So here, what we're seeing is that we don't want this x, but now thanks to having rearranged that original substitution, we can then swap it. So just make a bit of room and then we can swap that x. So this x can be swapped for half of u take away 5. And really constants like halves and 2s and 3s, it's better to deal with them right at the end. You just multiply your whole answer by that. So we can stick that half or any other constant at the front, because whatever we get as our answer, we'll just times it by a half. That's fine. Okay, so it's looking a little bit nicer, but still we've got this problem of u's and dx's. Before we go into the dx, let's just deal with the u. The u is a square root, and that's not going to be the easiest to integrate. So we're going to swap the square root for the power half, and that's going to be easier to integrate. And then I can expand that out as well. So I've got u times the u to the half, and then minus 5 times u to the half. So remember, u is really u to the power 1. So if I times that, that'll become 1 plus a half, which is 3 over 2. So let me write that on the next line. So just trying to make the inside as simple as possible to integrate. So I'm just going to times the u to the power 1 times u to the half. So that's going to become u to the power 3 over 2. And then you can guess the next bit. I've got 5 times u to the power half, which is just 5 times u to the power half. So actually, with both of those things, the substitution for the u and also expanding out the brackets, we've got something that's quite easy to integrate now. Almost. The problem is the dx. We can't have the whole equation with u and then have a dx. Dx means with respect to x. It means that you're going to be taking any x's and adding 1 to the power, but we don't have any x's, we only have u's. So we need to really get rid of this dx. I'll swap it. So let's go back to the original substitution and let's differentiate that. That way I'll get a dx. So what I'm going to do is just differentiate both sides. So I'll have du by dx. So if u is equal to 2x plus 5, then differentiate means du by dx will be equal to, and then just differentiate that. So 2x plus 5 differentiates to 2. Fantastic. And now treat it just like any other formula and try and rearrange it for dx. So that would mean I can take the dx to the other side. Now I've got du is equal to 2 dx. And then I just want dx on its own, so I can just times both sides by a half or divide by 2. So I'll have a half on this side times this side by half, and that will get rid of the 2. So now I've rearranged for dx, just treating it like any other formula. And that means I can do my final swap, my final substitution, which is this dx can be swapped for half du. And again, the half can be brought to the front. So that's there was already a half there, so this half gets times by this half, which becomes a half times a half is just a quarter. So let's write a quarter there. Okay, fantastic. So that has, with that technique, it is a bit of an advanced technique where you're using the substitution, but then you're doing the rearranging and you're differentiating it and rearranging it just to make sure that everything ends up with just u's. So now we can go ahead and we can integrate that. So just take a look at it for a second while I tidy the screen and just think, what would it integrate to? Remember, you did the warm up at the beginning, so your basic integration is more than enough to now integrate that. Okay, hopefully you're seeing that and it's not too much trouble. So let's begin. So we'll have a quarter can stay at the front, and then I will have brackets, square brackets to signify that I've now integrated. So add 1 to the power and then divide by the new power. So just take one bit at a time. 3 over 2 would become 5 over 2. So u and 5 over 2. And then you divide by the new power, which is 5 over 2. Dividing by a fraction, it's easier just to times by the reciprocal. So you just times by 2 over 5. Okay, first one's done. And then hopefully the next one's easier. Start with the power. If that goes up by 1, then I'll have u to the power 3 over 2. I've already got 5, so I just need to divide that by the new power. So you can do this on your calculator, 5 divided by 3 over 2, and you should get 10 over 3. Again, I've just multiplied by the reciprocal in my head, but you can do it on a calculator. And that closes the bracket. to signify that we have integrated. We could put a plus c here as well. And since we're not putting in any numbers, any limits, we can get rid of the square brackets. And that's it. Except we have our answer in terms of u. So, oh, I did forget when I took away the square brackets, so everything has to be times by a quarter as well. Okay, so now the only thing is to put back the u. The u is really 2x plus 5, so there's nothing too hard about that. We're just going to swap the u back for the 2x plus 5. So I'll do that here. So I'll have a quarter. So I'll take a copy of this and I'll just swap the u's and then we are done. So now swapping, I'll have a quarter at the front and then I'll have 2/5, 2x plus 5 in brackets to the power 5/2. And then you can guess the next bit. It's minus 10/3. And again, it's the only one change we're making is just bring the 2x plus 5 back in. So the u gets replaced by the 2x plus 5 to the power 3/2. That doesn't change. And then plus c. And if you had time, you could just neaten that up, times everything by a quarter. So that would become 2/20, which is be 1/10, and then everything else stays the same. But I'll just skip that last step and just leave it there, just as long as you're happy with the advanced steps that were before that. Okay, good. Let's just give you a moment to take that in and then just go through it in your mind for a few seconds, and then I will ask you the individual steps. So we'll go through that, but this time you will be telling me the individual steps. Have a think of what they were first. Okay, time for you to then just talk me through the steps, just one step at a time, just a few words to describe each step. Starting with the question. The question is to integrate this, which looks very horrible to integrate. I'm given the little bit of help that I can use a substitution u equals 2x plus 5. So do you remember, can you write in a few words what is the first thing I did? Okay, fantastic. So the u gets substituted where the 2x plus 5 is. Brilliant. So I can, wherever I see a 2x plus 5, I can just put u in its place. So that was the very easy step to start with. Fantastic. That wasn't enough though, because I've still not got everything ready. So what happened next? Brilliant. Rearrange the substitution. So we're trying to get anything with x in has to be swapped for u. So if I just rearrange that substitution, I'll get a half u minus 5 is equal to x. Then what do I do with that? Good, we can substitute that for the x. So we'll start to have everything looking reading with u's instead of x's. So this x can just get substituted for the half u minus 5. We did a little thing with the half, if you remember, which is quite important with harder integrals because it just makes them easier to handle. If you can write that down, what was that thing that we did with the half, and what else did we did? Good. We put it on the outside, so any constant we'll just deal with right at the end. It's not going to make a difference to the integrating bit. Okay, so it's looking good so far, but it wasn't enough. We still have to do something more. What did we do next to try and make it look ready? I think you might have mentioned it. Let's just check. So we've substituted, we've rearranged for x. Good. Okay, so this is the key thing that you must try to remember. What we need to do is somehow dx doesn't want to be there. So the only technique you have to remember is good. Differentiate the u expression. Brilliant. And rearrange for x. Well done. So when we differentiate, we get du by dx first. And that makes 2. But then if we rearrange that, we can get a half du is equal to dx. So I've differentiated, I've rearranged it. Now what? How's that going to help me? Good. You can use that to substitute away the dx. So the dx can disappear, and we can have half du in its place. Again, use the trick at the beginning of take a constant to the beginning, so that half can come forward times whatever's there already. So you've got a half already, so half times a half makes a quarter. So I can swap that with a quarter. Okay, and then the rest is basic stuff that you've done a lot already in earlier chapters of the course. So you just making this as simple as possible. You're just multiplying out, swapping the square roots for fractional powers, multiplying out, doing whatever you can do to make it nice and simple, and then you can expand everything out and then integrate. But the advanced technique was really up to what you've done now. Good. Okay, well done. You went through those steps really nicely. So now it's time for you to practice. Let me give you a practice question to try yourself, and then we'll see how you do. If you speed through the first practice question, try the second one as well. But just one is enough to make sure you can do it without my help, inshallah. And every 40 minutes or 1 hour, the Zoom window closes. So if you get locked out, then just come back in. Okay, so there's a substitution for you to make it easier, but you have to remember all those steps that you did before and try and integrate x times the square root of 1 plus x dx. Okay, take a few minutes to go through that. Okay, well done. The first one looks pretty good. Second one you might be getting a little bit stuck on. It's the same technique for the most part, but then you do have to always remember sine squared plus cos squared is equal to 1. So wherever you get stuck in these kind of questions, it's normally sine squared plus cos squared equals 1 comes to the rescue. So hopefully you've done the first bit. So sine x can be swapped for the u. But then you're thinking, well, hold on, I've got cos x here at the bottom and only sine x here. So if that's proving a little bit difficult, then just switch to the dx. Let's try and just differentiate, at least get rid of the dx first. So du by dx would be equal to cos x. So then what you can do is you can say, if you rearrange that for dx, so you know that the dx can now be swapped. So nothing different to what you've done before. Okay, so just going back a couple of steps because the meeting room closed. So here in this, the first bit was quite easy, swapping sine x for u, but then there's no obvious way to swap cos x. So what you could do is just remember sine squared plus cos squared, and that'll help you out. But let's just try and do the easy bit first. Let's say, okay, if the cos x is proving difficult, at least let me swap the dx. So dx, take the u equals sine x and differentiate, and you'll get u is equal to cos x. Then just rearrange that, and you'll get dx is equal to du over cos x. So that can be swapped now. So the dx can swap for that. And then what you have is what you have is cos x at the bottom times another cos x. So that can be cos x squared. So the cos x times the cos x, that's just cos x squared. So that will make it much simpler. Then nothing dividing on the bottom there, so I can get rid of that divide line. So now I've just got 1 plus u over cos x squared du. So although cos x was a bit difficult to get rid of, cos x squared will be easier. So you go back to the u equals sine x and just think, how can my sine squared plus cos squared help me here? Sine squared plus cos squared is equal to 1. So first of all, let's square both sides. So you get u squared is equal to sine squared x. And then remember that sine squared plus cos squared is equal to 1. Sine squared plus cos squared is equal to 1. So wherever we see sine squared, we can just drop it for u, swap it for u squared. So that sine squared can disappear, and I can just bring in the u squared instead. And now we're in a position to rearrange that for cos squared, and we'll have something we can swap. So just take the u squared over to the other side. That'll become a minus. And then I can now do the swap. So this cos squared x can be swapped for 1 minus u squared, which still looks a little bit tricky. 1 plus u at the top, 1 minus u squared on the bottom. Still looks a little bit tricky. So what you have to think of now is a technique beginning with D, and to do the one of the words in the technique, the name of the technique is a very famous shape, and that'll help you. Just try to think what that is. Type into the chat window if you can remember the technique. It's to do with factorizing when you have a minus in between and you've got both numbers on each side. Good, are square numbers. So here we can use difference of two squares. So we can factorize that 1 minus u squared into two brackets. It would be 1 minus u on the first one. Can you think what would be in the second bracket? Okay, it's just the same thing but with a plus, so 1 plus u. So that's called difference of two squares because 1 is a square number, u squared is a square number, and then minus, when you minus two numbers, that's finding the difference. So it's called difference of two squares. When you have that situation of a square number take away another square number, you can factorize it as into two brackets with one each bracket having a different sign. Okay, so that's pretty good, and that reason why that's pretty good is because the 1 plus u can cancel from the top and the bottom. So you're just left with 1 at the top because the same number divided by the same number is just 1. So if we write that out, we'll have 1 integrate 1 over 1 minus u du. So that's much easier to integrate. So let me let you finish that off. If you can just integrate 1 over 1 minus u. Okay, hopefully you remember that natural log of x differentiates to 1 over x. So you can use that to do the integration. So 1 over x would integrate to natural log of x. And then similar things, 1 over anything would integrate to the natural log of that thing, as long as you divide by what it differentiates to. Okay, so this would just become the natural log of 1 minus u. And then just think about 1 minus u. What does it differentiate to? Because we need to put that at the front as a divide. So 1 minus u differentiates to minus 1. So we just need to put 1 over minus 1 at the beginning. 1 over minus 1, that's just minus 1. Oh, we could just put a minus. Okay, good. So that one was a little bit tricky, but just see if you follow the main steps, especially the bit about using sine squared plus cos squared. So we're in this position here. We've swapped the sine x that was at the top for the u, and we've also differentiated and swapped the dx for a du. But now we're in this position where we've got cos squared x on the bottom. So how do you remember, how did we get rid of the cos squared x and replace it with some kind of u expression? Just type it in a few words if you remember what we did. Okay, maybe it was a little bit hard to follow, or you're just thinking of it. So good, we used an identity that you'll have to just drill into your mind. It's sine squared plus cos squared equals 1. So whenever you want to try and get rid of either a sine squared or a cos squared, remember sine squared plus cos squared is equal to 1. So to try and get sine squared, we square both sides of u equals sine x. So we end up with u squared equals sine squared x. Then we bring in the sine squared plus cos squared x equals 1 and rearrange it, and we end up with cos squared x is equal to 1 minus u squared. Okay, let's just check. We made it 1 minus sine squared, good. And then we used sine squared plus cos squared is equal to 1. And we swapped the sine squared for the u squared, good. So that enabled us to just swap the cos squared out, and everything else was in terms of u. Then we used difference of two squares. One of the brackets then cancelled, and the rest was hopefully easy to integrate for you. Good. Okay, good. More practice question coming up. Let's see if you can try. This is hopefully easier. That last one was a little bit hard, but this is more basic compared to how we started off. So can you integrate sine cubed dx using the substitution u equals cos x? Okay, if you finish that, we've still got a minute or two left, so if you finish that quickly, then just have a think of what's coming up next, where we have to integrate, but we're not given the substitution. So let me give you an example. Just have a think about that one in blue if you get a chance. If you're still finishing off question one, that's fine. Still got a few seconds. Okay, we'll just go have a look at the first one just to make sure that you're comfortable with it. So u equals cos x. We want to try to use that first, but unfortunately the original question doesn't have any cos x in it, so we can't really use that technique straight away. So what we'll do is we'll target the dx instead. We'll say, okay, well, let me try and get rid of the dx. So I differentiate du by dx. So if you can just type into the window that if you were to differentiate du by dx and then rearrange it for dx, what would you end up with? Okay, let's see if you are right. Good, you'd end up with the du on the top and on the bottom would be minus sine x. I'm just going to bring the minus to the front. So that means we can at least get rid of the dx. So we'll get rid of the dx and we'll have minus du over sine x in its place. The minus can come to the front, and that's why Aisha, you said to swap the signs, which is correct. Good. So then what we have is du divided by sine x, but here I've got sine x, which is cubed. So when you're integrating, it's sometimes easier just to bring that cube to what it really means, which is that the whole of the sine x is being cubed. And then you think, hold on, I've got sine x cubed, and then I'm later on dividing by sine x. So that means I'll have sine x cubed over sine x, and that can be made a little bit simpler. It's a bit like having x cubed divided by x, or y cubed divided by y. It will just turn out to be y squared. So you can say, okay, that was much simpler now. That's instead of being cubed, it's now going to be squared. And now hopefully you can see a way that before it was quite difficult to swap the sine cubed x for u, but now can you see a way where we can get the sine squared x, which is just sine squared now? Can we swap that somehow for u in terms, can we write it in terms of u somehow? Can you see a way? Good. You go back to sine squared plus cos squared equals 1, and then you swap whatever we were told for u. So let's write that there. Sine squared x plus cos squared x is equal to 1. But then if I know that the cos x is equal to u, then I can swap my cos squared for u squared. I can then rearrange for my sine squared, and then I'll be able to write it in terms of u. So that's very easy to do. Just take the u squared onto the other side. Good. And then we'll have something to swap with the sine squared, which is 1 minus u squared. And I think you'll be okay from there. Once you've made that swap, it's quite easy to then integrate. You'll have everything in terms of u, so there's really no problem at all. You just with things where you've got a plus or minus in between, it's really easy. You just take them one at a time. So you first think, okay, what does 1 integrate to? And you're integrating with respect to u, so it'll just become u. And then what does u squared integrate to? Just use your normal formula, add 1 to the power, divide by the new power, and then you'll have the answer. Good, and well done to Aisha for then once you got the answer in terms of u, once you've integrated, then put back anything that had u in your answer, anything that has u in your answer, just swap it for cos x, and then you'll be there. Okay, good. I'll give you two a 3 minute, let's say 5 minute break, and then we'll do a bit more on the next section, inshallah. Okay, assalamu alaikum wa rahmatullahi wa barakatuh. See you in 5 minutes. It's got to be a bit sharp. It's got to be exactly 5 minutes though, inshallah. Okay, assalamu alaikum. Okay, Bismillahirrahmanirrahim. We will restart in 1 minute, inshallah. Okay, we will restart in about 30 seconds, inshallah. That 30 seconds is, inshallah, enough time for you to just come out of this Zoom meeting, wait a few seconds, and then come back into a new Zoom meeting. So when I say just come out and come back in, let me just finish writing this question. Okay, Bismillah. I'm just gonna end this meeting, and then if you just want to come back in, we will restart straight away, inshallah. Okay, Bismillah ar-Rahman ar-Rahim. In the name of God, the most gracious, the most merciful. Well done for your work earlier on. We just want to add on a nice couple of little touches just to be able to extend the number of questions you can do on this topic. Just a couple of little things that if you can remember you'll be able to then access some more marks, inshallah. So first thing is, you're not always going to be given the substitution. So can you be able to figure out the substitution yourself? And generally it's quite easy. Generally, all you do is look for the complicated bit, and that bit that's under a square root or a power or something like that, or maybe the the trigonometry bit, and just use that as a substitution. So let's just show you for the first one. So what are you going to choose as a substitution? Just look for the bit that's in brackets or a power. We can see here the x plus 1 is there and it's cubed. You don't have to include the cube in your substitution. You just want to make it as easy as possible. So the u should be something simple, but it's going to make the whole question a lot easier. So we're just going to make the u equal to the x plus 1. So you can see here I've kept it simple, but it's in a way that's going to make this whole thing, this whole bracket, just turn into u, and then I'll just have u cubed. So that would be the substitution for the first one. See if you can guess what the substitution would be for the second one. Just type into the chat window. Good. So you're just looking for any of the trig bits or the... Yeah, good guess, and that's absolutely right. So the bit under the square root is very complicated at the moment. It's going to make it hard to integrate. So why don't we just swap it for u? So we can just say u is equal to 1 plus sine x, and that would mean we just have the square root of u, which would make it a lot easier to then deal with. Fantastic. Actually, I'll just keep that there so you can see the kind of pattern. And then the final thing, the final question here, what would we use to as our substitution in this one? Have a think. Once you see a couple of them, you'll see they're all pretty much the same. It's not too hard to figure out which bit is the substitution. Very good. It's just the bit under the square root here, so we would just use u as the 1 plus x. That would mean we can rewrite that as the square root of u, and then we can bring that to the top as u to the power minus a half, and that'll be much easier to work with. Good. So that's integration, that's getting the extra marks by choosing the substitution yourself. And then the next thing is, well, what if there's numbers on the limits? How can you deal with that? And actually, it's not harder, it's easier. When they put limits there, then you don't actually have to do as much work, because you can just leave everything in terms of u right at the end. You don't have to turn it all back into the x plus 1 or the sine x. That can just be forgotten about. So they're actually making it easier when they give you a question with the limits there. The only one thing you have to remember is that, well, these limits are for x, because this original question was in terms of x. So if you're going to if you get your answer, let's suppose you get your answer, you've done all your steps from before, and I'm just making this up, so don't look at it too carefully. But let's just say we had the answer, we integrated it, and we ended up with u squared minus 1 as our answer in terms of u. Well, we can't put the numbers 2 and 0 in, because those numbers for 2 and 0 were for x. So all we do is we take each number one at a time. Because they were numbers for x, we just substitute them in. So the 2 plus the 1, that makes 3. So that means my top limit would change to 3. So the 2 was fine if I was working with x's, but if I do 2 plus 1 to make 3, now I can use the 3 because I'm working with the u. Similarly, the bottom limit, 0, is only going to work if you're dealing with x's, so stick that in. 0 plus the 1 makes 1. So that means I can use a limit of 1 if I'm working with u. And then the rest would be easy. Just type that into your calculator. 3 squared minus 1. And then take away 1 squared minus 1. So it's a lot easier because you can just leave it in terms of u. And it's just that little substitution you have to do with each of the limits. Okay. Any questions or anything you want me to repeat on that? Just type in okay if it's okay, or not okay if it's not okay, if it was a little bit harder than I thought. Okay, good, mashallah, well done. So that means we can try something new. And this is to do with integrating when you have parametric equations. Looks very, very hard, but inshallah I will show you there's a very easy technique. You just need to see it once and you'll be able to use it, inshallah. So here we are trying to work out, we know we have to integrate because the question says work out the area. So we know we're going to have to integrate. We always use integration. The main purpose of integration is to work out areas under curves. Problem is they haven't given us just one equation. They've given us parametric equations. They've given us an equation for x, an equation for y, and it's these two individual equations. Normally, if they're really easy, simple ones, you can then do a bit of rearranging and you can end up with just getting rid of the t, and you just end up with your basic standard equation y equals something something x. And then you can just integrate that. But the problem here is that it's a little bit tricky because each equation isn't so simple. It's not just t, it's t squared, it's t cubed. So that means we want to use a different technique. We don't want to start rearranging it and getting rid of the t. That's not going to work. But we still need to integrate because the question was area. So all we do is we say, okay, well, if I did integrate, how would I start off the integration? And the way you'd start off normal typical integrations is that you write the integral sign. Then the equation is normally a y equation, so you write y. And you're normally integrating with respect to x, so you write dx. That's how you normally start it off. So no reason to do anything different here. That's exactly how we're going to start off, inshallah. But now we're going to bring in a little trick. We're going to say, well, dx, if I divide it by something and then times it by something, the same thing, then it's still going to end up as dx. I haven't changed the question. A bit like when you have a fraction and if you divide it by 2 and then times it by 2, it hasn't really made a difference because you've just divided by the same number, then times by the same number. So the same thing with the dx. Let me divide it by dt and then times it by dt. So that way, I haven't changed anything. It's still the same question, still gives me the same answer, but I've just made it look different. And the beauty of that is that now I can start substituting in. So if you think about the y, well, the y is t cubed, so that can go in place of y. dx by dt, I can work that out because all I need to do is differentiate with respect to t. So I can say dx by dt, and you can do this. Just take a look at the t squared and differentiate. That would be equal to 2t. So I can swap the dx by dt for just the 2t. And now my integration is looking pretty good because everything's starting to become in terms of t. And in fact, the dt is already there for you, so you don't need to change anything. So now you've got an integration which you can go ahead and do because everything's in terms of t and there's no problem. So we just need to put limits in. So the 0 and the 4 would have worked for x, but now we need to put them in terms of t. So just do a little bit of calculation. Just think, if x is 0, then what does my t need to be? Well, 0. And then try the other limit. So you've got x is 4. What does my t need to be? Here, t could be plus or minus 2. I'm just going to go with the positive 2. Sometimes you might have to do both. Okay, and that's ready to go. So let's integrate that. You got 2t cubed times 2t. Let's simplify first. That would become, the 2 can come to the front if you want. T cubed times t would be t to the power 4. So let's write. So this is the integral of 2 can come to the front. And I've got t to the power 4 dt. Integrate that isn't too hard. So that is just going to become 2 times, in square brackets, I forgot to put the limits, add 1 to the power, so that would be 2 to the power 5, and then divide by the new power, which is 5. The limits are 0 and 2. So then just type that into your calculator. So you've got 2 to the power 5 over 5. I'm going to just write the t bits. 2 to the power 5 over 5. Take away 0 to the power 5 over 5. And all of that times by 2. So just type that into your calculator and tell me what you get. Okay, hopefully you get a nice simple number. Good, just check it again. Okay, so with a bit more time, you could just type that straight into your calculator exactly as it looks, and you would end up with 12.8. Good. So let's just go over the beginning steps, because I'm pretty sure you can do the substitution at the end and the basic integration, but how did we end up with an equation where we're just integrating with t in there? That was the tricky bit. Oh, I don't know why it's not working today. Okay, so we ended up with integrate t cubed t times 2t and then dt at the end, but how did we get there? Let's just go back to the beginnings. So you tell me this time, one step at a time. We know we have to integrate, but how do we do it? How do we start? Good, excellent. So we don't panic, we just write what we normally write. We know we need to integrate. We need to integrate the y equation with respect to x, is how we normally work out areas of graphs on an xy axis. So that's exactly the first step. Well done. Good. At this point, we could even write the limits in. We know that x is 0 and 4. Good. And now comes the little trick that we used. Do you remember what we did then? What did we do next? Okay, so then we divide and multiply by dt because everything that we were given at the beginning was in terms of t, so somehow we need to get a t in there, and the best thing is just to do divide and times by dt. Excellent, good. And now if you look at each bit, each bit should be doable. So what comes next? Or what came next? I'm going to space this out a bit to give you a bit of a clue. Good. We find dx by dt, we find y, and we just substitute it in. So we can find y, that's quite easy. It's sitting here. So y is equal to t cubed, so that can go there. We find dx by dt. Well, that's so easy, we could probably do it in our head. Dx by dt is equal to 2t. So then 2t can go over here. And then the last dt just stays as it is because it's just saying that now we're integrating with respect to t. Okay, good. And then we just want to do two more things. One is to do with the numbers, and then one is what we always try to do when we're integrating. Just try to make it simple as possible. So the numbers first. What did we do with the numbers? Not sure what we did with the numbers. So the numbers at the moment are in terms of x, that those original numbers were x equals 0, x equals 4. But now we're dealing with t, so we have to use one of the formulas that they gave us to try and change those numbers for t numbers. So 0, if x is 0, we can put the 0 in for the x, and then t squared equals 0, and that must mean t is equal to 0. So we're just swapping the numbers instead of the numbers that worked with the t, we're just going to swap them for the numbers that would work with t. So 0 means that t is going to be 0, so that can go there. And then if x is 4, then what would t have to be? So if x is 4, then t would have to be 2 or minus 2, because square root of 4. So that would be, and I just used the positive one to make it simple, but you might have to use the negative one as well. In fact, let me check that now. Oh, okay. So whether you choose 2 or minus 2, they'll normally give you a clue in the question and they'll give you a limit on t. So when they write the equations, they'll normally have something like t has to be bigger than 0 as well next to it. So that means you can ignore any negatives. So that's the numbers changed. And then the next bit would have been, if you can remember, what did we do with the t cubed and 2t? Nothing advanced, just simple how you do it from the beginning when you're learning integration for the first time. We can't integrate normally just yet because you got something that is if you were to integrate normally right now, it'd be a bit difficult because you got t cubed times 2t, and you'd have to use some quite advanced technique for that because it's two functions timesing by each other. begins with S. Okay, next thing would seems like you've maybe lost that. Maybe I did that a bit too quickly. The next thing is simplify. So you don't want to make the integration more complicated than it has to be. T cubed times 2t. You can simplify that. So remember that's a times in there. So that's just GCSE maths. T cubed times 2t. That would be 2t to the power 4. So we can write that instead of two things timesing each other, we can just write that as one thing, and then that's much easier to integrate. If you did want to, you could take the 2 to the front. You don't have to, but it just makes harder integration easier. So now that's all you have to do, integrate the 2t to the power 4, which we did. Okay, so it looks like you need a bit of practice. Some of the steps seems like you weren't 100% sure on that, which is understandable because it's an advanced technique. So just remember, start off as normally, integrate y with respect to x, dx, do the little trick of dividing by t and timesing by t, and then take each bit and swap it for what you're given. So y can be swapped for the t squared, sorry, the t cubed. The dx by dt, you just have to do a bit of work, differentiate the x equation, and you end up with dx by dt. That's 2t. And then dt can be left alone. Change the numbers that were originally for the question in terms of x. Just go back to the x equation and think, okay, well, if x is 0 and 4, what does the t need to be? So if 0, t would be 0. If x is 4, t would have to be 2. And then just take a look at the integration that you got and just simplify it if you can. Here you can just times it, t to the power 4 dt. And then you're ready to integrate. Okay, you try one yourself. I don't know how hard or simple this one's going to be. There's not too many practice questions in the book here, so I've just chosen the one that looks similar, but it could be a twist. So parametric equations, t plus 1 squared. And then the next one is y equals a half t cubed plus 3. And the limit on t is that t has to be bigger than or equal to minus 1. And the limits on t are 1 and 5. Okay, so find the area under the graph. Okay, have a go. And I'm just changing that 5 limit to 4. That should make it easier when you get to the numbers. If you're getting stuck at a particular point, just type into the chat window what you did last, and then I can tell you what you need to do next. Okay, good attempt, but I've got a different answer when I've done it, so maybe I was wrong, but just check you're working out. Make sure you've integrated, because sometimes students can do the simplifying and then forget to integrate because they think that the simplifying was what the question was about. Okay, I'll give you a few more seconds to check your answer if you're trying to find where you might have gone wrong. Okay, looks like a very good attempt. So we'll just do this one line at a time if that's okay. So I'll say the step, and if you can tell me what your working is, what just the one line is that I say. So the first thing is when you substitute in the integral, you're putting in something for the y, you're putting in something for the dx by dt, and you're leaving the dt alone. What do you get as your first line? What does it look like? And no need to simplify or anything, just your very first line, what would it look like? Just type it in if you can. Should be starting with something like the integral of, and then in brackets, half. See if you can finish it off. So integral of half t cubed plus 3 t plus 1 squared plus t squared. Okay, so that's the bit that you need to get right. So the y just gets swapped for half t cubed plus 3. Nothing more, nothing less. So in brackets, half t cubed plus 3. We need the brackets there because we're then going to be timesing by the next bit. So then comes the next bit. So dx by dt, what did you get for the dx by dt? Here you're taking the x equation and you're differentiating it, and that has to go next. Okay, good. 2t plus t is what that differentiates to. You can expand it out and then differentiate. So then so now we're putting in the dx by dt, and notice I've got brackets around it because it's more than one bit, and so I don't want to get it confused. So I've got brackets half t cubed plus 3 for the y. That's just a straight copy. Times by, maybe I didn't make it clear, but these things are being times. The y times the dx by dt. Times by, so that's why I've got another pair of brackets, and then the dx by dt, and then the dt to finish it off. So that's what you should be integrating, but you can't really integrate that just yet because it's not being expanded and it's not being simplified. So the next step would be keep the integral as it is, the integral sign, but just try and expand those brackets to get it as simple as possible. You should end up with something t to the power 4 in there. So in that first answer, yeah, I'm not seeing any t to the power 4 just yet. So you need to expand that out and then just write down what your next line is. Okay, hopefully your first bit, when you do the half t cubed times the 2t, you should end up with t to the power 4. Hopefully your first bit matches. Let's see whether the rest of yours is right. Give you a few more minutes if you're still doing that. So I times the first bits, that's t to the power 4. Good, and now that's good. That's fully expanded, fully simplified. Now that is ready to integrate. It wasn't ready to integrate before. It was too complicated. So here, now you are ready to integrate. So you should, don't worry about the numbers just yet, the limits, but just integrate this and tell me what you get as your next line. Here, each bit should integrate quite nicely, quite easily. So just adding 1 to the power and then dividing by the new power. So I show yours looks fine. So then once you're comfortable that you've got the integration right, that you have simplified properly, and then you've gone ahead and integrated, then just substitute in. But you have to work out what your limits are going to be. The original limits were 1 and 4, but they were x's. So you're good at solving equations, so just try to use that to solve an equation. So if you know your x is 1, then what does your t have to be? If you know your x is 4, and okay, and okay, so I think both of you need to just take a look at that last bit in the integration. So if I can just take your attention to the last bit in the integration, we have to integrate 6 with respect to t. So any constant just gets integrated. When you integrate any constant, you just put the letter next to it, so 6t. So differentiation is opposite. The constants drop and they become 0. But integration is not like that. Remember, integration and differentiation are opposite. So the constant should become something. It'll become something with that letter, 6t. Okay, and then the limits for once you've remembered to put the 6, integrate the 6 to 6t, then you've got the integration ready. What are your limits? Just tell me two numbers. What will be my limits for t based on my x limits? I should be able to convert each one of them into a t. Okay, good. 1 and 0. So then you're ready. If you can put that into your calculator. Okay, so just work it out. And you should get something which is a very simple number, inshallah. Okay, I'll let you do that in your own time. So you should end up, if you've ended up with 9.45, fantastic, well done. If you haven't, then just go through, make sure each of your terms are right, and just be careful when you're typing it into the calculator. Good. Okay, well done for following it so far, mashallah. You are uh, entitled to a break now, so take a 10-minute break, and then we will restart for the last session, which is only a half an hour session, inshallah. And we will start that at 12 o'clock sharp, inshallah. Okay, see you then, inshallah. Assalamu alaikum. Okay, starting in a few seconds, inshallah. Bismillah ar-Rahman ar-Rahim. In the name of God, the most gracious, the most merciful. Mashallah, you made it to the last session, so that's good. Mashallah, the last session is taking what's called a differential equation. A differential means it's been differentiated. So imagine an equation that's been differentiated, and solving it means that you have to try to get back to the original equation. So to give you a very, very simple example of something you might have done in year one A level, but you didn't realize that it was called solving differential equations, is that if you took a very simple equation, say y equals x squared plus 2x, and you differentiated it, then that's how you start learning about differentiation and integration. You would have written dy by dx is equal to 2x. Actually, I'll put on a number here as well, plus 5. You would have differentiated it to get 2x plus 2, and then that's it. That's the end of the answer. Well, if you practiced that and you found that was really easy, then your teacher or the textbook might have asked you to do the opposite thing, which is say, if we give you the differentiated version, let's say if we say that dy by dx works out to be 3x minus 5, then can you work backwards and figure out what the original equation was? And normally that's towards the end of the year because you'd have learned integration by then. So to get the original equation, you would have just integrated. So 3x would have integrated to 3x squared over 2. The minus 5 would have integrated to minus 5x. We wouldn't have stopped there because the integration only gets us up to here, because the 2x can integrate, the 2 can integrate. But the thing that doesn't integrate is the constant that gets dropped off. So there's no real way of knowing what that constant is. So you just put plus c at the end. So that was that they call that practice of integration, but really what you were doing is taking what's called a differential equation, because it's an equation that's been differentiated, and you're solving it. You're going back to the original, what the original equation was. So that's what you have to do now, but it's a bit more advanced. The equation's a bit more advanced, that's all. So we have to find what was the original equation. If we end up with, after being differentiated, we end up with something like 1 plus 2x times dy by dx equals tan y. So let me show you the technique for this. It's not too hard. The technique is called separation of variables. Separation of variables. And what it means is that we just have to try to get all the different letters in their own separate part of on their own separate side. So if you think the equation's got a left-hand side and a right-hand side, we just want to separate it. So all the x's are on one side and all the y's are on another side. So let's try that. So separation of variables technique, I just take a quick look at this and I try to spot, okay, I've got some y's on this side, I've got some x's on this side, I've got then dy by dx, which has got a y and an x on this side. So generally you want to get rid of any fractions. So the first thing you want to do is treat the dx as a fraction, and we're just going to move it to the other side. So now that's looking a bit easier to work with. And then you want to think, well, I really want all the y's on one side and all the x's on the other side. So if I've taken dx to this side, I really want to bring the y's to the other side. So tan y can come onto this side and we can write that as a 1 over tan y. And then similarly, the x's can go to the other side, and that can be 1 over 1 plus 2x. So that's called separation of variables. Look how I've put all the x's on one separate side and all the y's on one separate side. And now, because everything's nice and neat and everything's just one letter on one side, what I can then do is integrate. But you integrate each side separately. So I'm going to integrate this side with respect to y, and this side I'm going to integrate with respect to x. It's a bit like doing two integration questions separately. Okay, so the left-hand side, I've got 1 over tan y. Remember from what you learned earlier in the year, 1 over sine can be written as cos sec. 1 over cos can be written as sec. Can you remember what 1 over tan can be rewritten as? So we can rewrite 1 over tan as cot. Good. So we can rewrite that as 1 over cot, because when we're integrating, we don't really want to have a fraction there if we can avoid it. So we can write that as cot y. Brilliant. And then I don't know what cot y integrates to, but whoever wrote the formula booklet in your exam does. So let's go to the formula booklet, and we're just going to look at what does cot y integrate to. So cot x integrates to the natural log of sine x. So cot y would integrate to the natural log of sine y, plus c, because constants drop out, so we never know what that is going to be. So we just write c. So let's write the integral of cot y works out to be the natural log of sine y plus a constant. And now let's do the right hand side. So remember that natural log of x differentiates to 1 over x. So similarly, 1 over x would integrate to the natural log of x. Here I've got 1 over 1 plus 2x. So it's going to be very similar. Can you think what it integrates to? The natural log of... Good, natural log of 1 plus 2x, except we then have to use the fact that it wasn't just x, it was 2x. It was 1 plus 2x. So we just have to put at the front, if you're differentiating, you times, but if you're integrating, you divide by something. Can you think what we divide by? So it's times 2 if you're differentiating. Here we're integrating, so we divide by 2. Good. So that's brilliant. That's the second side done. So we can do a half times the natural log of 1 plus 2x. And I'm just going to, I've used modulus signs on the left, so I'll just use modulus signs on the right. Otherwise, brackets is what I normally use. Okay, so that's modulus of 1 plus 2x, and then plus the c as well. Okay, then we can realize, well, hold on, I've got plus c on both sides. That means I've got a constant on both sides. The constant might not be the same on both sides, so I don't need it twice, but I do need it once, so I'll just have it on this side. And because everything else has got a natural log, I might as well just call this the natural log of c. Still a constant, but it's just easier to work with. Sometimes in your book you'll see it's called k, but we can just stick with c at the moment. And then we want to simplify. This half can be brought to the top, if you remember the power law of logs. So we can just bring that half to the front like that. Oh, actually, yeah. And then plus, when you're adding two logs together, then that just means So if you remember the rule, natural log of A plus natural log of B can be shortened to the natural log of A times B. So we can use that rule here. So that would just become natural log of 1 plus 2x to the power half times by C. We can bring the C to the front rather than have it at the end. And just need to work on it a little bit more, so you're trying to end up with just an equation as simple as possible with y and x in it. And what you notice here is both sides have got natural log on. So if both sides have got natural log on, we can just get rid of the natural log, cancel it out from both sides. You can only do that providing there's only one thing on both sides and there's nothing, no numbers or fractions in front of the natural log. So that's what it works out to be. So we have sine y is equal to some constant times 1 plus 2x to the power of a half. And that is how you solve a differential equation using separation of variables. So we haven't really solved anything. Solving here just means trying to find the original equation, which we have done. Okay, let's see if I can go, if you can go through the steps, and if my paint program lets me reverse all the steps. Oh, it's gone so far. I think it's because I keep pressing undo. Okay, so let's go back to the original question. So the original question, try to think of all the steps and then tell me one at a time what the steps were. The question was find the solution to the differential equation 1 plus 2x dy by dx is equal to tan y. Okay, over to you. See if you can type into the chat box just the first step. How did we start this off? Put the factors together, multiply by dx, good, and all of that is called separation of variables, getting all the variables onto one side with the same letter. So dx, definitely we multiply that across, and then we want to get the y's together and the x's together on each side. So the x can come across to this side, the y's can come across to that side. It's a times on one side, so it'll be a divide on the other, and then you have all the y's on their own and all the x's on their own. Well done. Okay, what comes next? What came next? Remember, we've got an equation that's differentiated. We want to try and get to the original, so we have to do the opposite. Not quite make it cot y. We can do that at this stage, that's fine. That would make things easier. So let me put cot y instead of 1 over tan y. That's fine. I actually did it a bit later, but it's better to probably do it earlier. That's good. So now what do we do next? Remember, it's a differential equation. It's been differentiated. We're trying to get back to the original. So what do we do to get back to the original? Okay, you're missing the key thing. What do? We integrate. Good. So we're trying to get back to the original. So we integrate we integrate both sides. So I just write an integral sign on both sides first, and then I take each side separately and I integrate. Good. So the left-hand side integrates to, if I remember correctly, natural log of sine y plus a constant. And the right-hand side, can you remember what that integrates to? Okay, natural log of 1 plus 2x, natural log of 1 plus 2x, and then there is a half which comes at the beginning because if it's not x, if it's 2x, then you have to divide by that too. So it's a half at the beginning. Okay, good. And then we have to add a constant. And then if you remember, a constant plus a constant or a constant on both sides, we only need it on one side. We don't know if it's the same, so we can't cancel it off, but we'll just write it, and then it's easier to write it only in this case because we're dealing with natural logs. Normally you can leave it as c, but here it's better to write it as natural log of c just because everything else is logs. And then we took the half over to here. Do you remember what came next to that? See, we can't just get rid of the natural logs at this stage because to do that you have to have only one of them on each side. So what do we do? Okay, so what we use here is it's not take it to one side, but combine. So when you got a natural log, when you got two log terms, a log A plus a log B, you can use the rule that you can combine them into one. Log A plus log B is the same as log A times B. So we can just combine them into one. That's the logarithm laws that you have to try to be very quick to spot. So here we can just combine them into one. 1 plus 2x to the power half times by c. So all of that is just now combined into one natural logarithm. The c can come to the beginning, just easier to work with if it's at the beginning. Okay, good. Do you remember what came after that? We've got to a stage where we've got just one natural logarithm on both sides. Okay, so then we can just cancel out, yeah, we can cancel out the natural log. What you really do is you raise both sides to the power e, base e, to a power of e, but it's much easier just to think of it as if you got natural log on both sides, just cancel out the natural log. And there's your final equation. Notice it doesn't have to be perfect, as in it doesn't have to start with y. As long as you got y on one side and all the x's on the other, that's fine. Even if you had it combined a little bit, that's okay. But as long as there's no dy by dx and it's simplified as much as possible. Good. Okay, because time is a little bit short, I'm going to move on to the next one. So I just want you to see how we apply this technique to a word problem. So these word problems, they do tend to turn up in your exam quite frequently, and we're going to use the same technique you just learned. I want you to see how you can use it. So just take a minute. I'll stop talking. Just take a minute to read the question. Just read it only and have a think. Okay, hopefully that's enough time to have a read of the question. So the main thing is we are trying to get from the differentiated version of the equation to the original version of the equation. That's all. So we're going to use exactly the same technique. We are going to start with the differentiated version. We're going to separate the variables, and then we're going to integrate both sides. So let's separate variables. What do you think comes first? What step do you think comes first? Any ideas what to do first? Good. We are going to multiply by dt, so let's take the dt to this side, and now I've got something very nice and simple. What else can I do? Remember, separation of variables is the name of the technique. Good, divide by 3p, so let's bring the p's to one side as well, so I can put 1 over 3p on the left. Okay, even though there's nothing here, that's fine, that's actually correct. So it looks like nothing, but it's really 1. Okay, good. What next? This is the bit where you got a little bit hesitant on in the example I showed you. So this is the critical bit for you. Remember, overall, you're trying to get from the differentiated version to the original version. You've nicely separated the variables, but now what? Fantastic. So integrate both sides. So integrate this left-hand side, put an integration sign there, and put an integration sign on the right-hand side. Here we don't have anything between the dt, so I'm just going to fill it in with a number 1. You don't even have to do that, but just for the purpose of learning, it's really 1 times dt. Okay, good. And then have a go. Take it one side at a time. So the left-hand side, what do you think happens what do you think I'll get when I integrate 1 over 3p? One over third natural log of 3p. That's brilliant. Well done. So you get natural log of 3p initially because 1 over x integrates to 1 over x, and then you're just putting a dividing by 3 at the beginning because of the 3p, not the p, plus a constant. So you put plus a natural log of c. And then on the right hand side, this should be an easy one. Integral of 1, integrating 1 with respect to t. Notice it's with respect to t. Okay, fantastic. You just end up with t on the right hand side. We could put t plus c, but we've already dealt with the c because we put log c on the left hand side, natural log of c. Good, excellent. So from here, What we want to do is just take a sneak look at the answer. We want to try and get it all into the format that they've got here. Notice they've got 3t and we've only got t. So what we're going to do is we're going to say, look, I can get rid of this 1/3 by timesing by everything by 3. So I'll get rid of the third. I'll times everything by 3. So that will drop off. This would become 3 times the natural log of c, and this would become 3t. So 3t is exactly what I need. 3 times the natural log of c. Remember, c is just a constant. It's a number that we don't know that we know is going to be there. So whether I call it 3 times the natural log of c, 3 times a constant, or whether I just call it a constant, the 3 doesn't really make a difference. So uh, just for the making it nice and easy to work with, I can cross off that 3. I can just leave it as natural log of c. Okay, good. And now, do you remember a little bit about the log laws and what you can do here? Okay, good. We can combine that into 1, so that would become the natural log of 3p times c. 3p times c, so 3pc. Here they probably called it a instead of c, but we can deal with that when we get there. So just combining that into 1. Okay, good. Now, remember, you're trying to get something to look like this. So we don't have any natural log in here. We have an e, but we don't have any natural log. So we really want to get rid of the natural log. Any ideas how we can do that? Okay, if you haven't seen this before, a very, very good technique to learn is that if you want to get rid of the natural log in an equation, what you do is you raise both sides to the power e. So it's like writing e, and then whatever you had on the equation just goes there, and you're raising both sides to the power e. So these are your two original parts of the equation, and you just put a big E as your base. Let's see if you knew that. Log base A power B C. Okay, I think that's another technique as well, but I'm just going to make it easier. So I'm just going to make myself a bit of space, and I'm going to put both sides to the power of E, because the idea is that the natural log and E are opposites. So a big E, and now this can be the power on this side, and then a big E, and then your 3t can be a power on that side. So let's just make them a bit smaller so it's obvious there is a power. So that comes here, and then the same thing on this side. The 3t is now a power on the E. Okay, looking good so far. And the reason we do that is because E and natural log are opposites, so they cancel out. They cancel out, and all you're left with is the 3pc. So we can cancel out the e and the natural log, and all you're left with is what was the power. But it's no longer a power now. It's totally, the natural log and the e have totally dropped out. So it's 3pc is equal to e to the power 3t. Okay, looking good. You should be okay to do the last bits yourself. So trying to get to here. So what do you think should happen next? Divide by 3c, perfect, that's very good. So we will divide by 3c, so that way we will have only p on the left. But when I divide by 3c, I'm just going to keep it separate. So the way I'm going to do it is I'm just going to make a bit of space, and I'm just going to have 1 over 3c. Good. And then 1 over 3c, if you look at the equation that they've given you, they're not using the letter C, they're using the letter A. So what they've done is that they've just swapped 1 over 3C for a new letter, which is A. So we can write that if you want. We could say let A equal 1 over 3C as like a substitution if you wanted to, but you don't normally need to bother. With constants, you are flexible because you can change the letter if you want halfway through. It doesn't matter. So we're just going to change it to A. So that's pretty good. The only next bit to do, and inshallah it won't take too long. So what you have to do is try to figure out what number we can have for A. So we go back to the beginning and we're just going to do a bit of substitution. So let's take a copy of that equation. And what we're going to try and do is figure out what number we can use for A. If I can substitute in a P, if I can substitute in a T, then I'd be able to get the A. The T is from the word initially. Initially means at the beginning, and the beginning means time is 0. So I know that T equals 0 can be substituted here. But what about P? Is there anywhere in the question where I've got a value for P? Fantastic, 8. So I can substitute 8 into the P. So if you can do that and then rearrange and then figure out what A is. So just rearrange that and then tell me what do you get for A. Okay, well done, it's 8 again, so that's perfect. A is equal to 8, which means we can finish off the equation now. We can say the final equation is that P is equal to 8 times e to the power 3t. Okay, so just to remind you of the technique, we start with the equation they've given us for dp by dt. We separate the variables, get the p's and the t's on different sides, take the dt over, and then we integrate both sides. We integrate both sides, and we use the log laws if we have to, and then we try to make it as simple as possible. When we've got it as simple as possible, read the beginning very carefully to try to get a number for two numbers that you can substitute in. And then if you substitute those numbers in, you'll get something you can put in to finish off the equation properly. Okay. Okay, well done, mashallah. That is integration, some of the tougher techniques in integration. Today you've gone through quite a lot, mashallah. So you did the integration by substitution, and then you did the integration of like parametric equations, and then finally we just did separation of variables. So go away and practice, 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 and inshallah Allah give you success in your exam. Assalamu alaikum wa rahmatullahi wa barakatuh.